Did you hit record? Okay. I'll begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students, this opportunity we have just to meet together and study your creation, study math. And I just pray you be with us. Help us again, Lord, to glorify you, Lord, in what we do. You know I pray, Lord Jesus. Amen. All right, so let me start out with something easy. Here's a theorem. It's actually kind of a little theorem. You might call it a theoremito if you're a silly person. Let's say U and V be a subset of a vector space V over a field F. All right. Then, and also just to keep things interesting, and let's assume U and V are not equal to 0. Okay. I guess I could prove an even smaller theorem before this one, right? So that's that if 0 is an element of a set S, that implies that S is linearly dependent. It's a very little theorem, as you can see. Fine. Take all the fun out of it. Check it out. If 0 is an element of S, then 1, the scalar 1, times the 0 vector is equal to 0. Therefore, that is a non-trivial linear dependence because there is a non-zero scalar such that the linear combination, the scalar multiple of a vector is a very silly kind of linear combination, but it is nevertheless a linear combination. And so there you have it. If 0 is in the set, there's a non-trivial linear combination in the set. So therefore, S is linearly dependent. Okay, so if 0 is in the set, it's linearly dependent. Yes, sir?
How would you call that even smaller? How would you call it even smaller?
Ooh. I don't know. Did you add another ito to it? I don't know. Is it a theoremito? I mean, it's like it's a micro theorem. I don't know. Yeah.
What is that bracket?
I'm sorry?
On the end of the theorem? Nope.
Here?
The right, all the way to the right. What is that close to?
Oh, nothing yet. I was in the middle of writing, and I got distracted by my little theorem. Okay, so we got if 0 is in the set, it's linearly dependent. The proof is just what I wrote on the board. Okay. All right. So if there's if you have two vectors in the set, so U and V in vector space, assume they're non-equal. Let's assume they're non-zero vectors. If either of them is zero vector, we're done. It's linearly dependent. So that's not interesting. Let's assume they're non-zero. Okay. Then let's see here. UV is linearly dependent. If and only if there exists some scalar k in the field such that V is equal to k times U. Okay. I wanted to prove something a little bit easier before we jumped off the deep end over there. All right. So let's see here, proof. Assume UV is linearly dependent, right? What's that mean? You can write C1U plus C2V is equal to 0, where what? At least one of C1 and C2 is not equal to 0, right? At least C1 or C2 is non-zero. Right. So in fact, you can easily argue that they both have to be non-zero. How do you do that? Let's see. Suppose Suppose C1 is not equal to 0, but C2 is equal to 0. What would that tell us? Right, we would have what? We have C1 times U is equal to 0. But what did we get? What was one of our basic things we derived from the axioms of a vector space? If you have the product of a scalar and a vector is 0, either the scalar is 0 or the vector is 0. Right? But the vector is assumed to be non-zero, so what is this force? This force is C1 equal to 0. Right? Yeah. That's my point, is C1 can't be 0, so this is a contradiction. So this is obviously a contradiction, right? Hence what? C1 is also, C2 rather. C2 is not equal to 0, right? You notice that you don't have to contradict the thing you assumed is wrong. All you have to do is find a contradiction to something you're looking at, right? It just so happens I get C1 is equal to 0, whereas the thing I incorrectly assumed here was C2 was 0. Doesn't matter. I mean, if you say something is true towards a contradiction and you find out that your father was Hitler, then if that's not true, your assumption was wrong. And that's proof by contradiction. Is that Godwin's law? I don't think Godwin's law really applies to linear algebra lectures, but maybe today. You guys don't know Godwin's law? Something like any internet argument will devolve into some discussion of Nazis within some certain length. I forget exactly the technical statement of Godwin's law. Yeah. No relation to Godwin here. But anyway, I digress. So we have both constants are non-zero, right? Then what? So we can say, okay, so we have, so from this, from star, what do we get? So you can solve for, I'm trying to solve for v, right? So solve for v. V is equal to minus C1 over C2 times u. So set k equals to minus C1 over C2. And we're done with that part of the proof. See, I've shown that linear dependence implies that there exists a constant such that the one vector is a scalar multiple of the other. Okay. Now, this is a biconditional statement, right? So what else should I do? I should suppose that there exists some scalar k in the field such that what? Let me be greedier. We can add something to this theorem that will make it useful. What can you say about that constant k? Let's make it the most useful theorem we can state. What did we get here about k from my argument? It's not just any constant. It's a non-zero constant, right? Certainly the ratio of non-zero things is still non-zero. So in fact, you can say, you can add the condition that k not equal to 0. That'll serve us well in going the other direction. So suppose there exists k in f, k not equal to 0, such that what? V is equal to ku. Well, we're almost done already. This implies what? This implies that v minus ku is equal to 0. But that's a linear dependence, right? Actually, as Curtis defines it, even this is a linear dependence. So you might wonder why I write anything else. Anyway, whatever you take as being basic linear dependence, clearly we have a linear dependence between u and v. So u and v is a linearly dependent set. All right? And so there you go. Any questions about this one? All right. That brings us to the big story for today, which is this theorem over here. So guys, what we're doing today is I'm trying to show you sort of the big guns of the theory of linear dependence. And so this is really bedrock foundational stuff for pretty much anything we do past this point in the course. So, whoa, it survived. So I'm trying to get into the details here, even though I probably will regret it after I do. So here they are. Here's the theorem. This is Theorem 5.1 in Curtis. It's Theorem 3.5.2 in my notes. I think the big difference between Curtis and my notes is that Curtis uses S, where I use a W. And also, one of the things you might, at some point, once I gather my wits, I will make a compendium, a translating, a dictionary between Curtis and my notes. There is some difference in notation, right? He likes to use just a capital S for span. I more confusingly just write span. So, but of course, just writing an S does have its advantages. If you start leafing through like 10 different linear algebra books, you'll probably find 5 or 6 different notations for span. But I think this is fairly common. Anyway, here you go. So if you form a subspace W, in particular by the span of these n vectors, n as in nanu, inside some vector space over a field, all right? And if you look at another thing, a subset of that vector, subset of that span, B1 through Bm, all right? And you have more vectors in this subspace than you have in the generating set, right? Then it follows that the subset B1 through Bm is linearly dependent. For example, if I have a span of 3 vectors, and then I take a subset of 4 vectors, is it linearly dependent? I don't have to think about it once I understand this theorem. The answer is yes, it's linearly dependent. If I have a subset of 10 vectors, and I look at the span of 10 vectors, right, and I look at a subset of 20 vectors, it's going to be linearly dependent. Game over, end of story. All right? So we're going to prove that in generality here. And the proof is by induction on n. So you'll forgive me if I wrote this before class. The reason I had to do that is just my shoulder's hurting, and so I got to slow down a little bit. And anyway, here's where we start. So induction on n. So first case is n equals to 1. Right? N equals to 1. So n equals to 1, we'd have the span of 1 vector. Right? Oh, by the way, I don't think he really has in mind the 0 subspace, but this still makes sense for the 0 subspace. If this is the empty set, then the span is 0, and if something's a subset of the 0 set, it's 0, so it's linearly dependent. So this also makes sense if the generating set is empty. But whatever. We'll start with n equals to 1. So for n equals to 1, we have 1 vector, and of course, if a is equal to 0, well, then we're done, right? Because if a is equal to 0, the span is 0, so any subset of the 0 vector set just containing 0 vector, 0 vector. I didn't even write that down, right? So suppose a is not equal to 0. Oh, I'm sorry, I wrote it up here. I'm an idiot. Duh. So if W is a span of A, right, and you have a subset of B1 through Bm in W, that means that every one of these B's is a scalar multiple of A. That's the only kind of linear combination you can take of just one vector. It's just as scalar multiples, right? So then there are 2 cases. Either A is 0 or A is not 0. If A is equal to 0, then it follows from these equations right here that all of the B's are 0, right? But I don't even need all that. Even if one of the B's is 0, we already know it's a linearly dependent set by our micro theorem over here. Sorry, that theorem is very trivial. Pun intended. All right. Now, if A is not equal to 0, that means that there has to exist a coefficient not equal to 0, because you see, if there wasn't a coefficient not equal to 0, we'd have trouble. If this coefficient, all of these were 0, then that would force B sub j to be 0, which would be a contradiction. So it must be that there's at least one coefficient non-zero, right? So if there's that one non-zero coefficient, lambda, lambda j, then you can look at this particular linear combination right here. So this is a trick. What you do is you take lambda j times b1, and then over here I take minus lambda 1 times bj. The reason I do that is because I read it in Curtis. No, the reason we do that is because that gives us lambda j times lambda 1 minus lambda 1 times lambda j. But these are numbers in a field, they commute, and so you get 0. In other words, this linear combination gives you a linear dependence of 0, but it's not a trivial linear dependence. It's a non-trivial linear combination of the b's, which gives you 0. Well, game over. That means that b1 through bm is a linearly dependent set. And so concludes the proof of the n equals 1 case. So we're trying to prove that this is true for all n in the integers, positive integers. So what we got to do is do induction. So next step, we suppose inductively the theorem is true for spans of n minus 1 vectors. All right? So what's that mean? And then we're gonna look, well, we'll use it in a second here. So what we're going to do is we're going to consider a subset of m, b1 through bm, subset of the span of n vectors. All right? And we're going to suppose that m is greater than n, because that's the precondition. That's the precondition over here of the theorem, right? So we want to assume that. So what does it mean? This star equation here, it gives me lots of things. It says that there exists constants in the field, lambda ij. Now, I and j are from where? I mean, 1 less than or equal to I less than or equal to m. 1 less than or equal to j less than or equal to n. All right, that's the range of the I and the j here. So we get these linear dependence, of each b in terms of the a's like this. There have to be these linear combinations of a's that reproduce the b's. And I'm just going to call this whole thing Pac-Man. Whoa, that was an interesting noise. So, let's see here. What's the meaning of lambda ij? Think about it in terms of these equations. Like, lambda ij are the coefficients which are attached to which one? They're attached to aj, right? Like, lambda blah, blah, blah 1 is attached to a1, right? So the second coefficient attaches it to the, So, if, for example, lambda I1, right? If lambda I1 was equal to 0 for every I, so if lambda I1 was 0 in this whole thing, all the way down, what would that mean? Think about that. Well, I mean, if these are gone, right, the next thing in here is lambda 1, 2, a2, right? So you'd still have every b was a linear combination of a2 through an, and the same thing for I equals to 1, 2, all the way to m, right? So if this condition is met, that means that this subset, it's a subset of this span. So it's a subset of the span of n minus 1 vectors. But what are we assuming inductively? We're assuming the theorem is true inductively. That means that if I have a subset, right? Now, there's a little bit more to say here. I need actually to apply the induction hypothesis. What do I need? Think about it. I need m greater than what? Not n, but what? N minus 1, right? That's what we need to apply the induction hypothesis. But, I mean, so, yeah, so the fact that m is greater than n also gives us this. So we're okay. Not a problem, right? If m is greater than n, m is certainly greater than n minus 1 as well. So we can apply the induction hypothesis, and we get that b1 through bm is a linearly dependent set in the case that all of these are 0. All right? So, what if they're not all 0? That's the other case, right? Either they're all 0, or there's at least one that's not 0, right? So if there's even one of these in the first column, as we're looking at this Pac-Man system, if there's even one non-zero, then it's a different story. But what we'll do then is suppose that lambda I1 is not equal to 0 for some I, all right? For the sake of not writing I like 100 times in the next 10 minutes, we're going to relabel the ith equation and the 1th equation. We're just going to row swap them. And so without loss of this is what this means, without loss of generality. So by the way, this means suppose. That's suppose if you were wondering. Although me talking about it is undoing the goodness of the thing. Without loss of generality. We can assume that lambda 1 is not equal to 0 by just putting it in the top. Just relabel. All right, so with that relabeling, we have lambda 1 is not equal to 0. And now I must write. So, if we with that relabeling, what do we have for A1? A1 is equal to what? 1 over lambda 1, right? Times what? Times B1 minus lambda 1, 2, A2 minus minus lambda 1n an. Do you guys agree? So what did I do? I just took the first equation here, right? And I solved it for what? I solved it for A1. It's actually a lot like the little theorem I did right here. Actually, the idea of this theorem is not so disconnected from what we're doing right now. Really, the heart of it's the same. We'll put that there. All right, let's see here. All right. So then consider. I may not even do anything with this. I'm just showing you could do that, all right? I'm not sure I even use this, but to me, it was the next logical step. I'm not sure it actually is what we need to do, though. So following Curtis again, what we're going to do is we're going to look at B2 minus lambda 2, divided by lambda 1, B1. All right? What is that? Well, B2 is what? B2 is lambda 2, A1 plus lambda 2, it sounds funny, A2 plus lambda 2n, an. And then what? Minus lambda 2, over lambda 1, B1. Lost my place. Oh. All right, so I don't want to multiply that out. I just want to write down the answer. So what do we get? Look at B1. So think about just, stupid. So what I'm doing right now is I'm just looking at this, right, which is B1, and I'm taking the right-hand side of that. Here's the B1 again. I'm just taking the right-hand side of that, and I'm multiplying it by this coefficient. That's all I'm doing, okay? That gives you lambda 2, over lambda 1, lambda 1, A1, minus lambda 2, over lambda 1, lambda 1, 2, A2. Sorry, this is amusing me more than it should. Minus minus lambda 2, over lambda 1. If we're dividing by it, it's lambda 1, okay? That much is sure. Lambda, man, we should have called oh, it's too late. Should have called lambda 1 something stupider, like, I don't know, alpha, lamb chops, no. Okay. Jess, you missed your opportunity. That would have been the ideal time to interject 7. Let's see here. Yeah. Okay. But you see that we can collect terms now, right? See this? What can you do? Well, the beautiful thing about this is it's the same trick as the n equals 1 case, right? We're really modeling the inductive step in the same argument that was used over here in the red-green thing, right? Like if you look what we did there, the way we canceled this term and that term out by the sort of like anti-symmetrizing it. It's the same tricky thing here. See, because now this term here and this term here are what? They're gone, right? Those are cancel. Those are canceling. It's the same thing. And all you're left with, right, is lambda 2, 2. Oh, sorry, let me collect terms here. Lambda 2, 2 minus lambda 2, 1, lambda 1, 2 over lambda 1, 1, parentheses, A2 minus, minus lambda, 2n minus lambda 2, 1, lambda 1n divided by lambda 1, 1, a sub n. Ay, ay, ay. All right, so again, following Curtis a little bit, we'll call this thing lambda 2, 2 prime, and this guy here is lambda 2n prime. The point, of course, is that these are just, these are things in the field again, right? Because certainly if we take a reciprocal of elements of the field and subtract it from another element of the field, we're again in the field again, right? Because the field's a commutative ring at the base of everything, so it's closed under addition, right? And division makes sense here. Long story short, what is this? This is a linear combination. I mean, this is what? This is an element of the span of what? A2 dot 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 AN, right? So what we've just shown is that this particular vector here is in that span. All right? You can do this trick again on the third and so forth and so on. So here I'll write it down. So generalizing this a bit, for the jth one, now Curtis actually has the third one written out. I'm just going to go ahead and write the jth one because I'm trying to be confusing. All right, so lambda, you're like mission accomplished. All right, well, thank you, I guess. Let's see here, bj. So bj minus lambda j1 divided by lambda 1, 1, that will cause a canceling of the a1s as you look at the linear combination. And you'll just be left with basically the same thing, but this time you'll be left with like lambda j2 minus lambda j1, lambda 1j divided by lambda 1, 1, a2, and then minus minus lambda jn minus lambda j1 lambda 1j divided by lambda 1, 1 an, which of course is an element once more of the span of a2 through an. All right. Therefore, collect our thoughts here. We have we've got b2 minus lambda 2, 1 over lambda 1, 1 b1, right? And so forth and so on, all the way down until we get to finally bm minus lambda m1 over lambda 1, 1 bm, right? This is an element of what? Well, this is a subset of the span of A2 through AN, right? So of course this is how many vectors? This is n minus 1 vectors, right? Counting, how many are there here? Yeah, m minus 1 as in m as in mummy. All right, so consider we have m is greater than n. We're assuming that from the outset, right? Right up here. We're still working on that induction. M is greater than n implies what? M minus 1 is greater than n minus 1, right? Hence, by the induction hypothesis, we have that, oh man, I'm very tired of writing that. Let me call this thing B. we have B is what? Linearly dependent set, right? And then what does that tell you? So what? Then there exists mu2, mu3, all the way out to mu_m, not all 0, right? Such that what? Here we go. We get mu2 times b2 minus lambda 2,1 over lambda 1,1 b1 minus mu3 b3 minus lambda 3,1 over lambda 1,1. Oh man, you know what there's a lazier way to do this. What we should have done is we should have set lambda 1,1 equal to 1 without loss of generality. Just rescale all the equations to do that. This is not lazy enough, this argument. Oh well, anyway, here it is. You spent big bucks to get this book, so I want to make use of it. Let's see here. I hope you didn't spend a lot of money to get the book. Let's see here, I'm joking. Why is this equal to 0 and why are these not equal to 0? Because the B is a linearly dependent set, right? We earned that from the induction hypothesis. And then what can you do with this equation? It's the part you guys like. Just calculate, right? Compute, reorder, collect all the things with B1. What do you got? You got minus mu2, lambda 2,1. I'm going to put the minus out front. Mu3 plus u3, lambda 3,1. I factored the minus out. Plus da-da-da-da, plus mu_m, lambda, m1, all divided by lambda 1,1, b1. And then you got yourself mu2, b2, plus da-da-da-da-da, mu_m, bm equals to 0. Oh, I thought this moment would never come. I feel like this proof takes forever. We're done. Because now we have shown that there is a non-trivial linear combination of the b1 through bm, which is 0. This establishes the linear dependence of the subset b1 through bm. And then that concludes the induction. And then, so that concludes the induction step. Therefore, this theorem is true for all n. Yep.
Okay, I have a question. This might be dumb, but in big B squiggly whatever thing of this is that yes. Okay, so it says B2 minus lambda, then it's B1. So why is it not Bn minus B?
Oh, that is, you're absolutely right. Thank you, Christina. That is supposed to be a 1 place Slayton. Hey. Sorry. I've yet to hit a student. Sorry, apparently my shoulder muscles aren't quite right. Sorry about that. Not trying to scare you in that way. Let's see here. Yes, just with math. Now, my goal in here is not to scare, by the way. I am. It's not like there's someone always watching me. Always watching. It's not like that. Stupid thing. Sorry. Ross is the best, yes. All right, if you don't know what we're talking about, it's okay. It didn't have a childhood, yeah. All right. We had to work kind of hard to get this theorem, but now that we have it, we can use it. So, the next theorem, in some sense, I think is more. This is an interesting theorem. Don't get me wrong. It's so intuitively. To me, this theorem is very intuitively obvious, right? if you read my notes, I've summarized this argument in like 3 lines. Right? But the details are involved, as you can see. The next theorem, 3.5.3 in my notes, or I think maybe it's 5.2 in Curtis, I can't remember. Here it is. If you have a vector space V over a field F, and you have that if you have V1 all the way out to Vn, and if you have W1 all the way out to Wm, all right, and these are subsets rather of the vector space V, such that the span. Oh, something else here. Oh, what else? I need something about these subsets. I'm assuming that these are linearly independent, okay? So if I have 2 linearly independent subsets of a vector space such that their spans are matching, such that the span of V1 through Vn is equal to the span of W1 through Wm, then punchline, m is equal to n. All right. So how's the proof go here? So suppose that we have, as the theorem states, these two linearly independent sets, all right? And let's suppose that, of course, V1 through Vn is a subset of the span of W1 through Wm, right? And suppose, what do we want to suppose? If we're gonna make use of this monstrosity I just spent a lot of class time on, we should assume what? As I currently have it assembled, we should assume n is greater than m. Sorry, it would have been better pedagogy if I had reversed the v's and the w's. My apologies. But I'm tired of writing, so it stays. Then what? Thus, V1, Vn is not linearly independent by theorem just proved, whatever its number is. I can't read it from here. 3.5.2. I need some glasses. Sad. A set cannot be both linearly independent and not linearly independent at the same time. That is a contradiction in its purest form, right? Contradiction. So therefore, n is not greater than m. How are we going to get the other non-equality? Likewise, W1 through Wm is a subset of the span of V1 through Vn with m greater than n implies a contradiction, very similar contradiction, so therefore n is not less than m. You put those two things together, you got n equals to m. Es bueno. So therefore m equals to n. In view of this, we make a definition, which I already told you last time. Well, maybe I didn't. Last time I told you there's something called a basis, right? What was a basis? I'll remind you. Beta a subset of a vector space V over a field F such that beta is linearly independent and the span of beta equals to the whole space. Or you could also do this for a subspace, of course. Then beta is called a basis for V. Right. Technically, it should be an ordered set. We have a sense of ordering here. What this theorem we just proved up here says is that if you have a linearly, all right, so in other words, if, for example, if beta equals to W1, likewise through W, say, K, all right, and W is the span of W1 through WK, all right, and this is linearly independent. If you have a linearly independent set and this W is formed from the span of those vectors, then this let me call it beta sub W. Beta sub W, that's a basis. That's a basis for this subspace W, right? And what we say is the dimension of W is equal to the number of the cardinality of beta in the finite case. So in this case, it's K. That means W is a K-dimensional subspace. So the number of things in the basis for a vector space is called its dimension, provided that there exists a finite generating set. If we can span the vector space by some finite set of elements, then it's said to be a finite dimensional vector space. This theorem 3.5.3 states that the number of elements in a linearly independent spanning set is not up for grabs. It's an invariant of the vector space. It's characteristic. It's the same no matter what choice of linearly independent spanning set you choose. So that's very nice. Now, I should warn you, the concept of basis is field dependent. So, I mean, to be more careful, you might say this is the dimension with respect to the field F, where I'm assuming, of course, this is a span with coefficients in F. To give you a little bit of contrast there, you could look at this. You could, on the one hand, look at the vector space V, say the complexes. And so the point set's the complex. I'm taking the field to also be the complexes. Then what's the basis for V? Well, V is just equal to the span of 1, right? Because if you take any Z equals to X plus IY in the complex numbers, right, then X plus IY is equal to X plus IY. It's kind of stupid, times 1, right? In other words, it's in the span of 1. Right, but in the quite contrasting this, if I take the same point set, if I take V equal to the complexes, but if I take the field to be the reals, that's a different vector space, right? And in fact, in this case, if you take Z equals X plus IY, we don't have we can't use X plus IY. See, this is in the field, right? This is an element of the field, which in this case is the complexes by our definition. But if my field is the reals, I can't do that, right? And I'm stuck with this. So, I mean, what I have is I have X times 1 plus Y times I, right? So this is an element of the span over the reals of 1 and I. So a basis for the complex numbers as a real vector space is in fact 1 and I. One and I are linearly independent in the real sense. 1 and I are linearly dependent in the complex sense, because I is just equal to 1 times I. That's a linear dependence in the complex sense. I'm not allowed that. if I'm working in the reals, because I don't have I as a scalar. So over the reals, the complex numbers are two-dimensional. Over the complexes, so the dimension of the complex numbers over the reals is 2. Up here, the dimension with respect to the complex field of the complex numbers is just 1. So the concept of dimension very much is based on your choice of field. Okay. I wanted to show you an example, a little bit more calculational today. I'm not sure I have time though. By the way, it's good if you're reading Curtis, but you should also be reading my notes. If you're not reading my notes, you're trying to take this course the hard way. Like, my notes have, I think, a lot more examples than Curtis, right? And some of them are even correct. So, of course, I leave all those errors in there for you to find. I found a few in the stuff we're doing right now that you guys haven't told me about yet. Oh man. Well, I have this, I guess that example I was going to show you fits better with next class anyway. What I'm going to do with the remaining couple minutes is show and tell. I'm going to show you and tell you, oh, I don't need that. I think I got 3 minutes of battery life. I'm going to show you and tell you about the other theorems that I have not proved today that are of similar difficulty to prove. Next time, I'm going to talk to you guys about the structure of solution sets. So we're going to take a look back at equations, and we're going to try to understand how we can think about solution sets to equations as subsets, as subspaces. So next time I'll cover how to find like the basis for column space, the basis for null space, the basis for row space. I had an example prepared for today, but obviously I don't have time. Come on, what is that? Oh, circle wheel of death. Did you hear that? Interesting. Where was I? So come on. So I have really we have done the hard part in section 3.6, guys. Is what we did today. The rest is kind of just easy, frankly. And so I've called this a tale of two maths because I found two different ways to understand this material. My old way did not give the argument I just gave you today. There's a different argument based on the trace. So this was anyway, once we get these theorems as further consequences. If you have a linearly dependent set and if you take one vector away and it becomes linearly independent, that means that the one you removed is a linear combination of the ones that you have left. Very intuitively natural, this theorem. Every finitely generated vector space has a basis. Very nice. If you have a span, finitely generated vector space with generators A1 through AM, then you can remove things from this until it becomes linearly independent. In other words, any generating set you can always pare down until it becomes a basis by removing vectors, which is very nice. And then Curtis's final theorem, if you have a linearly independent set of vectors and you have something that's not a basis, then you can keep adjoining vectors to that set until it becomes a basis. So if it's not a generating set yet, you can just keep adding things outside the span until you get until you get something. So the way I proved this thing previously was based on this argument here. Come on, where'd you go? I want my hand. Where'd the hand thing go? Oh, phooey. Goodness gracious. So I have a direct proof that if you have a linearly independent generating set, right, and if you have two of them, one has m, one has n, this is a calculation which directly shows that m has to equal to n. It does so by writing one basis in terms of the other, which is analogous to this stuff we were doing in here. And after a while, you get this matrix equation that says, like, the product of two matrices is equal to the identity. And one is the identity of order m, the other is the identity of order n. Take the trace of both sides, you get m equals n, because the trace of AB equals the trace of EA. That's the argument I've given in past years. It's rather different than what I did for you guys today. So I would encourage you to read this section. And I'll probably do one of these theorems at some point. I won't do all of them. We won't have time. But these are so important to try to internalize not so much the proofs necessarily, but certainly the statements of the proposition, like this one. This is what Curtis was also saying, right? If you got a vector space and it has dimension n, well, no, this one we didn't have yet. If you have a vector space of dimension n, if the set has more than n vectors, it's linearly dependent. If the set has less than n vectors, it doesn't span the space. You're like, we already had these theorems before, right? But we had them before for column vectors, before quiz 1. This theorem is for arbitrary vectors. They could be, as long as it's a finite dimensional vector space, it could be set as a set of polynomials, it could be set of matrices, antisymmetric matrices, polynomials in 3 variables out to order 10. I mean, there's tons and tons of things this covers that are not column vectors. Anyway, with that, I will shut up. Your next homework, I know that you're sad right now because you don't have linear homework to work on. Don't worry, I will fix that. It will be out soon. I know Danica in particular is sad because she no longer has homework to work on. Oh, look, a tear, figuratively. So anyway, you can cut it off. I don't have anything more useful to say.